Okay. Boom. These are the first two. Bohr diagram for MgO and a Bohr model for Cl2. So we got the Bohr model for magnesium, the Bohr model for oxygen. We drew the arrows for how they transfer. I want to see all these steps. And then we redrew the two ions, because this is an ionic compound. Excuse me, a metal and a non-metal. Cl2, same thing. Bohr model for chlorine, another Bohr model for chlorine. But because these are both nonmetals, they're going to share that one pair. So then you redraw the two outer shells overlapping where those two electrons are going to share. There is no need for the brackets because these guys don't become charged, because there is no give and take. These are what these two should have looked like. Comments, questions, concerns on any of this? This was homework from Friday. Okay. The next two would look like this. So the next one I gave you a slightly larger formula. I said BeF2. So we have to draw a beryllium. That guy. Beryllium is Roman or atomic number 4, 5 neutrons. Then 2 Fs. There's one, there's one. The fluorines. Each of the fluorines have room for 1. So one is going to go to one is going to go to the other. And then, because of the physics that you learned in grade 9, like charges repel, opposite charges attract. So you'd redraw this. One of the fluorines is negative. It would be next to the positive, and then the other negative would be over here. You've got to use the positiveness and the negativeness. Opposite charges attracting, like charges repelling, to draw them in this order. This is what it should look like. This is water. Water was one of the examples I gave you. But you have to go through the steps again. Let's go valent compound. And then we've got the Bohr model for Li2O down there at the bottom. 2 lithiums, 1 oxygen. Each lithium's going to donate 1 to the oxygen, and then again, you set it up so that the negative is sandwiched between the 2 positives. Questions, comments, concerns on any of those things? Put your phones away, please. You don't need them. All your friends are here. Anyone outside this room is dead to you until 1 o'clock. And then they can be alive again. They're in their own class. Okay. 5 practice questions. There you go. Comments, questions, concerns? Okay. We're all good with all of this. I see lots of writing, which means some of us didn't do our homework. Okay. Which means if you're stuck, come see me at lunch. We're moving on. Here we go. So, I told you guys on Friday that there was a guy who came after Bohr, around the same time Bohr came around, and said, that's a lot of work. Don't want to do it. There's a lot of unnecessary work we don't have to see. So this guy's name, a photocopier for whatever reason took off, or the printer took off his first initial. As a chemist, his name was G.N. Lewis. I don't know what the G and the N stand for. Doesn't matter. G.N. Lewis developed a system that he thought was better than Bohr's system. You stay on this page. I want to flip back for a second. If you look at what I just had you draw, for all of these Bohr models, the only electrons that actually matter are which ones? Which ones move around? Which ones get shared? Yeah, the outer ones, the valence shells. So G.N. Lewis came along and he developed a system of arranging dots. We used dots before, so that wasn't really a change. What he did was he arranged those dots around the symbol for an element to represent an atom and its valence shell as it prepares to bond. He said, well, if the only thing, bond, B and D, if the only thing that matters is that outer shell, those are the electrons that are going to move around. Those are the only ones we have to draw. And if I just put the symbol down, it doesn't matter what the protons and neutrons are. You can go look them up. The only thing that's actually involved in... Do you forget your book at home?
No, it's right in here.
Oh, okay.
I couldn't name it for no.
Okay, that's fine. I was because I do. If anyone forgets their booklet, I do have extras. We can take the loaner copy just so you have something to write in. James, put your phone away. None of you need to be on your phones. Put them away. If I have to ask you again, I'm going to start taking them away and sending them down to the office. So here's his system. I'll show you a Bohr diagram, and then I'll show you the Lewis diagram. Both are the same one. So for homework, you guys had to do fluorine. Yeah, you have to do fluorine twice because it was beryllium F2 or BeF2. So this is what the Bohr diagram for fluorine would look like. Fluorine is Roman numeral, atomic number 9. So that tells you how many protons there are. You go look at the periodic table. You say, okay, cool. The mass is 19, so the thing's got 10 neutrons. It's in the second row, so it's got 2 shells. It's in column number 19. No, it's in column number 17. So it's got 7 in the outer shell. 1, 2, 3, 4, 5, 6, 7. And then every shell under that is full. The inside shell can only hold 2. The innermost shell can only hold 2. So there's your Bohr model. Again, you do enough of these. Doesn't take you very long to do. But the best scientists are the really lazy ones. So Lewis came along and said, I can do it better. The Lewis diagram looks like this. It says, I don't need to look everything up. Fluorine is F. We can look up the protons, we can look up the neutrons, they don't matter. And now let's just put dots around it to represent the outer electrons because the inner ones don't matter. So because fluorine is in the 17th column, it's going to have 1, 2, 3, 4, 5, 6, 7 electrons, and you're done. You place them the same way we did the Bohr ones. You start on one edge, you treat them like a little box. You start at the top or one of the sides. It doesn't matter. But you pick a side and you start there. You go around 1, 2, 3, 4. And then you start pairing what remains. 5, 6, 7. There's only 7, so you're done. Yes, my grade 9s are obsessed with me saying 6, 7. I don't know why. Clearly, it's a meme. What does it mean? Does it have any meaning other than being from the one song that I found when I Googled? Okay. Okay. One of the answers to their questions this morning was 6/7, and it blew their mind. Okay, so Bohr diagram, Lewis diagram. Arguably, obviously simpler. Way less to draw, especially once you get down to some of the really massive elements. So the only thing you have to remember is that the group number is tied to the number of the valence electrons. So group number 1, the first two columns are easy. Group 1 and group 2, there's 1 and 2 valence electrons. Where things get a little weird and where I see students making mistakes is 13, 14, 15, 16, 17, and 18, because there is some nuance there. You just need to look at the ones column, though, is the thing to remember. Group 13 has 3, 14 has 4, 15 has 5, 16 has 6, 17 has 7, and then you got to be careful with 18. Does every element in group 18 have 8 valence electrons? Which one does not, Jihad? You just said no because I asked the question? You are right. So then which one is the one that makes you think that? Okay. we looked at numbers for how many electrons could fit in each shell. It was tied to, where's my periodic table? There's my periodic table. If you look at the periodic table, the first shell can only hold 2. 1, 2. So helium's the problem when we start drawing Lewis diagrams for these things, because helium doesn't hold 8. It only has 1 shell. That inner shell can only hold 2. These guys, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Neon and argon each hold 8. But then once you get down here, this guy will have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And we said when we were going through this the first time that those outer shells would hold 2, 8, 8, 18. And so the number of electrons in a shell is tied to how many elements are in the row that you are in. So it's not just 8. Group 18 is going to have 2 or 8 or 18, and there's actually bigger numbers in there too, depending on how many electrons are in the row. Or how many elements are in the row. Helium obviously being the one that's going to screw us up, because we don't actually draw Lewis diagrams or Bohr diagrams for anything bigger than calcium. So the rules here are really quite straightforward. We want to write the symbol for the atom, or the symbol and the charge for the ion. We want to determine the number of valence electrons for the given atom or ion, remembering that the valence electrons for the atoms comes from the group number. Ions are interesting because you start with the group number of electrons, and then if the ions are positive, what will the ion have done to the electrons? Give her whose shoe is that? Thank you.
She needed a phone massage.
No, she did. Not now. What do positive ions do with their outer electrons? I have empty desks all over the class. If I have to split you up, I will. Positive ions. Like when an ion becomes positive, what does it have to do to become positive? Lose. It gives them up. And it gives up, if you look back to what we did, what does it give up? It gives up the entire outer shell. What are the ones that we just drew? There. Here's an example of one we did. Beryllium. Beryllium wanted to become positive 2. It had 2 in the outer shell, gave 1 to fluorine, gave another one to this fluorine. So if you're drawing the Lewis diagram for a positive ion, it's going to be empty. Empty if the ion is positive, or full if it's negative. There's no counting you have to do. Again, depending on whether they're metals or nonmetals. We want to place the valence electrons around the atom or the ion starting at the top, just like we did with Bohr diagrams, moving north, east, southwest until it's half full, and then pairing them up. So, which I did, and I demonstrated all of these steps when I did the fluorine example right there. Fluorine as an atom, it's in group 17, has 7 electrons. You put the symbol 1, 2, 3, 4, 5, 6, 7, and you're done. So, let's flip the page. Do 4 examples, then I want you to crank out some before we turn this into an exercise in compounds. So examples, the chlorine atom. A chlorine atom is the symbol for chlorine. You would have looked at that last year, is Cl. Hopefully you remember that. Chlorine is in what group? 17. So anything in groups, or the ones that we look at in group 17 are going to have 7 valence electrons. 1, 2, 3, 4, 5, 6, 7, and you're done. Nothing fancy to do there. Beryllium atom. Beryllium is Be. What group is beryllium in? Group is the column number. You can look at any of the periodic tables around the class or flip to the inside cover of your notes. Where's beryllium? Group 2. And it's in row number 2, so you'd have to separate them out. There's a beryllium atom and you're done. Next one's bromine. And I've specified that the thing's an ion. So let's take a look at bromine. You want to start it the same way. There's the symbol. I've told you that this thing's going to be an ion, so now let's go find the charge. Bromine, there it is. Charge is going to be -1. The only thing we really care there is that it's negative, so let's put a -1 there. And just like the Bohr diagram, stop drawing on my desks, please, gentlemen, or you can wipe them all down. Erase what you're drawing on my desk. If your buddy's drawing on the desk, when he reaches his pen over, stab his hand. He can wipe up all my desks if he wants. Put the square brackets around it like we did before. It was day 1, my course outline. Don't draw on my desks. Bromine's negative, so what's it going to do? It's going to gain, which means it's going to totally fill. You don't even have to count. You just have to fill it up. There it is. The other side to this is calcium. Calcium as a Bohr diagram is terrible. It's huge. It's in row number 4. It would have 4 shells. You'd have to fill it all up from the inside. But as a Lewis diagram, as an ion, it's easy. The symbol for calcium is Ca. If you take a look at the periodic table, you'll see the thing has a charge of +2. And the positive ones become positive by giving everything away. So you throw square brackets there and you're done. There are no valence electrons. They are all gone. I don't have a pack of baby wipes for you guys to wipe down the desks with. That's it. Okay, crank out these 9. On your markets, I go. Draw me some Lewis diagrams for those 9 atoms or ions. You got a periodic table in the inside front cover. There's 4 of them off the classroom. Draw me some Lewis diagrams. The valence shells only ever be out of shells, sorry. So there are 25 electrons in that outer shell, but non-poles. So when we introduced you guys, the first thing I said to you was, come off with wrong. 4 models here, did you get them out? It's wrong. That's not how we get rid of it.
So I'm obviously going to do this. I'm going to use it.
They are useful,
I'm least right here.
but there is a better way.
No, I'm checking right here.
No, even better to take them on my computer. I can't demonstrate it. Show you.
What are you doing? You literally pulled them.
Because you've asked the question. I'll show you what they look like. So the Bohr model is wrong. Here's how things actually look.
Yeah, I was kind of confused. I didn't even know what the whole chart thing was. So
this is what things
It looks like a flower.
it does.
Are we gonna be drawing these?
No, this is Chem 11. So this is, that's not even all of it. Here, let's do this one. So this is what the shells actually look like. So the reason the inside shell can only hold one, or only hold two, is because you have one spherical shell, and every one of these shapes has space for 2 electrons in it. So that one can only hold 2 and you're done.
But why do we hold like more?
The next row can hold 8 because there's one of these. This is a level 2, but these 3 are also level 2s. So one of them is like 2 balls this way, 2 balls this way, 2 balls this way.
So it like wraps.
It wraps around in weird shapes. So you've also got some of these other weird shapes, like these ones. This is 3-dimensional, so it goes like this, and then like an up and down axis. So for these ones, this doesn't happen until you get down into that row that contains potassium. So K, the 4th row, starts to look like this. You still have the shell.
Is it like a jawbreaker, like it layers around?
Well,
Does it
yes, yes. They overlap and they are there.
I thought it was like a solar system, like it's just like flat.
They are not a solar system. That's where the Bohr model was, and it's useful, but it's broken. So then with gold, you're actually way down here. Gold looks like. So this is a way to demonstrate it. Anything that says S is a sphere.
Where does it say S?
So here, where it says 1, S2, S3, S4, S5, S6, S7, S.
Where do we find these on like the thing?
So these letters, the S's, the P's, the D's, and the F's, represent
Different shape?
those different weird shapes that I just showed you. So for this guy,
That is cool. I didn't know.
this is gold. It would have, it would be full up to here.
One,
Then you go here. See how they're all paired?
yeah.
This is all paired, but there's one guy right there. Gold only technically has, if I look at the periodic table for gold, even though it has a ton of, what looks like a ton of valence electrons, the charge on gold is +1,
Which is that one?
which is that one right there. It could also be +3 because of, which does it give up the other 3 from? They would have to come from, it's a phenom. I don't know where they'd come from. That one, I don't know how that would happen. But the +1 ion comes from giving up that. That would be the valence electron right there, which is why on this Bohr diagram, that's how they've drawn it.
That's smart.
This is a Chem 11.
I can't look up board diagrams. Now I'm gonna be thinking of a flower in 3D shape.
You should. And they're really quite cool. Mr. Easton, so he teaches the Chem 11, Chem 12, and IB Chem. He has models of what all of these orbitals look like up against the window in his classroom. It's really quite cool. So then this has, so then if we look at, I'll do a simpler one, like oxygen. If we look at oxygen down here,
What's right there?
the reason,
Easier. Which one?
yeah, the reason oxygen becomes -2 is because those two are paired, those two are paired, those two are paired. There's the space.
Why does it lay them out like that instead of pairing them together?
That I
They're
don't
all
know.
around.
I don't know. But the reason I want you guys to pair them top and bottom is because these two are one of the pairs, these two are one of the pairs, and then these two are your loners.
Why aren't they paired up together? If they're both together?
Because electrons are both negative. Like charges repel each other, and so they push each other away and to exist in different spaces.
I thought they were like this.
Because the p orbitals look like this. P orbitals.
It's like the proton.
They look like this. So there's 2 that go this way, 2 that go this way, and 2 that
They're
go
gonna
this
be
way.
Two unfinished. Right?
Yeah, because they push each other apart. So there would be 2 in, there'd be 2 here, but then there'd be only 1 here and 1 here. Because they
Like
want.
half of it instead of like a full.
Okay, gentlemen, why are we standing? Why do we have our phones out? And why are we not working on what we're supposed to be working on? Okay, put your phone away. You have 9 Lewis diagrams. You should be done already, technically.
That should be two.
No, you're doing other stuff. You're actually learning things. So with these guys, the other screwy part of this is that these aren't physical containers that exist. Because, I mean, like the way you're picturing it is you're picturing the nucleus and you're like these boxes that exist. The boxes can exist because you have overlapping boxes as you get bigger and bigger and bigger, right? Like there's boxes for each one of these as the element gets larger and larger and
Like
larger.
different shapes.
Well, all of the S ones are the same shape. All of the P ones are the same shape. Like they'd still have bulb. But from this one to this one, they get larger.
So like the
So it'd
darker the color, like orange, red, green.
All of the ones of the same color are the same shapes. They get larger as you go up the rows. But all the blue ones are the same shape. All the yellow ones are the same shape. The red ones, the green
The
ones.
rows as in like valence shells, right? Or like the shells around. The
Yes. Technical. Well, in this model, they're called energy levels. And so the electrons at the inner one will push outwards because they're also negative on the next level. This is why these ones are at a higher level than these ones. So then these two, the electrons all spread themselves out. But again, they're not containers. It's a cloud. It's called a... How are you mathematically? Math skills good?
Yeah.
Okay. It's called a probability density cloud. It means that if you went looking for the electron, it would most likely be in a space shaped like this around the nucleus. It doesn't have to be, but it's most likely in that cloud. That's what those shapes mean. The most likely places you'll find the electrons.
Like in that cloud.
And yeah, you're grade 10, so you've done it in Math 9. You know how you graph linear equations in grade 9? Like here's the equation, you graph the line.
Yeah.
These shapes are created when you graph a particular equation in 3 dimensions.
Is it gonna be physics?
At that point it turns into physics. I did it in my 3rd year physics class. We graphed those equations using software, and all of a sudden, like, so the way my physics teacher taught it was he said these are the equations that we're playing with. They govern music, they govern heat distributions, like how heat and temperature move throughout a room and throughout objects. And he said, let's see what happens when we graph these things. So we graphed these things, this one particular equation, and we graphed it in 3 dimensions, and out popped chemistry. So the math, these are dictated by a deep underlying mathematical framework for the universe. Blew my mind. It's awesome. So at that point, chemistry is the shapes, where they come from is the math, and that's physics. So that is why when doing something like gold, it doesn't actually have 25 valence electrons. 1.
So
Because
all of them have one.
no, I mean every element's going to be different, right? Like that was gold. You looked at what's next to gold. Gold is cadmium. And then I will answer Ashreen's question. CD is cadmium. Oh, it's yeah, CD. So this one, if you look here, would have 2 valence electrons. That pair. If you look at the charge, cadmium's +2. It's whatever this outermost shell is. And because that's a 5 and that's a 4, you can see in the name there, those 2 would be the valence shell. You don't need to know any of that until chemistry next year, and even then you still only have to know very little. But it's pretty cool stuff. How can I help you?
Is this right?
I'm going to go over all of this very shortly. And some short answer is some of them are right. So yes, 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 and yes. Those 5 are right. These 4 are incorrect.
What do I do with them?
I will. I can show you right now, or I can show everyone in like 30 seconds.
Okay.
I'm gonna go over all of them right now for everybody. That was not the end of my lesson for today.
Okay.
Oh yeah, no. We're gonna do, I was just asking. I would have done it already, but Jihad has some good questions. No, I'm gonna go over all of them right now. I'm just gonna cruise through. Okay, so gentlemen and ladies, you should be done already because that should have only taken you a couple minutes to do, so I don't know why you have nothing with that stage. I'm going to go show you what these things are, because this is not the end. We don't care about Lewis diagrams for individual elements. We're going to turn these things into actual compounds and then do stuff with those compounds. So we're going to go through those 9 right now, just using the instructions that I gave you. Yeah. Yeah. Yeah, so I'm going to demonstrate these right now. Okay, so the Lewis diagrams. You're going to need a periodic table handy, or again, I got 4 or 5 of them. 3 useful. I have 4 total. 3 useful, 1 less useful. So, Lewis diagrams for this. First one, carbon atom. What is the symbol for carbon? You got to find it on the periodic table. It is C. Okay, cool. It's an atom in the question. So we don't care about the charge. We don't need to put brackets down. We just need to draw the thing. What is the group that carbon is in? 14. So all you do is you look at the ones column there. Group 14, what number is in the ones column? So 4, so that's the number of electrons. And you have to space them out like you're drawing around the box. So that was, you had 4, but you got to space them out. So you draw 1, 2, 3, 4, and you're done. Because the thing's in group 14, and the little number's right there up at the top, you don't need to do any counting. Like you can see, carbon's right there. Group number 14. Only got 4 electrons in it. Those are the 4 that we draw. Argon. Find it on the table. You might have to look name by name until you figure out. If you're not familiar with the periodic table, you can find it. It'll take some time. The big one at the front doesn't have the names on it, but the paper ones I've given you do. Argon is in group number 18, and it's not helium. Helium's the one you got to be careful with. Argon has 8. 1, 2, 3, 4. And now we start pairing. 5, 6, 7, 8. You only pair once you've spread them out as much as they can be spread out. Ooh, next one's an ion. Gotta find lithium. So you hop on your periodic table, you look for lithium. Lithium's up there in the top left corner. Lithium is Li, and put the charge right away. It's +1. Because we're asked to do the ion, you put the charge, you put the square brackets around the thing, and you're done. There's nothing else to do. Because for lithium to become positive, it has to give away the outer shell. So there are no electrons to draw, you're finished. Magnesium, symbol is Mg. It is in group number 2. So we draw 1, 2, and we're done. You keep them, you do not pair them until you have put a single one everywhere around the 4 sides of the box, and then you can start pairing them up. There is one exception to that, and it's helium, which we're going to do right there. Hydrogen atom. Hydrogen is symbol H. It's in column 1. Boom. Up there on the top left. Helium atom. Helium is, again, I said it a couple times and I'll say it again. Helium is the tricky one because helium is in group 18. And so all the time I see, okay, 18, 8 in the outer shell. That is only true for neon and argon. For helium, the shell is full, but it's only the first shell. First shell can only hold 2. So those ones have to go side by side. Helium's the exception. And things get weird as we go below argon, but I'm not going to ask you to draw anything bigger than calcium because things get silly there, as Jihad saw. Because she asked some good questions. And there's a good reason why we don't talk about them in grade 10, because things get silly. Sulfur ion, letter G. Sulfur is, symbol is S. It's up there in the top right-hand corner. kind of ion to sulfur form? What is the ionic charge for sulfur? -2. So you put the -2, you put the brackets around it, and because it's negative, now you have to fill sulfur. 1, 2, 3, 4, 5, 6, 7, 8. Sulfur gets filled up. The phosphorus atom is P for phosphorus. It's an atom, so we don't care about the charge. We don't care about the square brackets. It is in column 15 or group 15. 1, 2, 3, 4, 5. And then strontium is Sr. It's an ion, so we want the charge, which is +2. The square brackets, and because it's a positive charge, the electrons are all gone. You're done. That's all you had to do. Comments, questions, concerns on any of that? Going once, twice, thrice. We're good. Sold. Okay. So it doesn't. Yeah, this is not where it stops. The whole point of Lewis diagrams is to take the Lewis diagrams and extend them. Because Bohr diagrams, like you stay on this page. I'm going to review. This kind of sucks. These are not nice and clean to draw. And so what we want to do is as the atoms get larger, the compounds they form get larger. And sometimes when we start to draw some of the more ridiculous covalent compounds, they can get really, really, really big. Things like, and we do it in chemistry all the time because we draw things like sugar. Table sugar is glucose. Actually, it's sucrose, but table sugar is sucrose. Glucose is a sugar that your body needs all the time to live. If you don't get glucose, your body will start to die. And so because we want to see how it reacts, it's one of these things that we draw. And drawing a glucose molecule, glucose looks like this. C6H12O6. There are 24 atoms there. If we were doing a Bohr model of this compound, it would be huge and disgusting. But Lewis gives us a nice, clean way to do it much smaller. And I'll show you what it looks like here in a second. So the compounds are what we want to do now. There's two different kinds of compounds. If you remember from yesterday, Friday. First, we got to figure out if the thing is ionic or covalent. If it's ionic, that means you've got a positive and a negative, or a metal and a non-metal. If the thing's covalent, it means you've got two negatives, or a non-metal, non-metal. You cannot have two metals. They do not bond chemically like this. Or Irvin, if you could sit at a desk so your back is not facing the television. I don't care what desk it is, but I don't want your back to the notes I'm trying to give you. We go through the same steps that we did for the Bohr models, but they're easier because the whole thing is smaller. You still have to draw the Lewis diagrams for the reacting atoms separately first. That is no different. They take a lot less time, though. If they're ionic, you still show the transfer, and you draw the ions in brackets. If they're covalent, this is where the Lewis diagrams are really, really powerful. Because instead of drawing overlapping orbitals, what you're going to do is you're going to do this. You are going to redraw the atoms with lines, replacing the shared electron pair. And I'll show you what I mean. You don't have to redraw the whole thing with overlapping circles like you did for the Bohr diagram. Here is what this will look like. So, two examples. You want to draw the Lewis diagram of LiF, lithium fluoride. So, Li stands for lithium. It's up there in the top left, which makes lithium a metal. And fluorine's up there in the top right, makes fluorine a non-metal. So this is going to be an ionic compound. So we follow this first set of instructions. We got to draw these guys separately. So there's lithium. It's in group 1. You're done. Here's fluorine. I know I'm going quickly. This really doesn't take that long. Fluorine is in group 17. You got to find it on the table, but it's up there, top right. Column 17. So we're going to draw 1, 2, 3, 4, 5, 6, 7. And now you can see what's going to happen here. Lithium is going to do what? Without even looking up the charges, we can see what's going to happen here. Oh.
Attention all staff and students, activate lockdown immediately.
There it is.
Activate lockdown immediately. Activate lockdown now.
Leave your stuff where it is. Then we'll curl up in that corner together. Yeah, leave your stuff where it is. Move over there.
Where you going?
This is kind of an awkward seat out on the table. It's all around. I mean, it is technically speaking. If this was an actual lockdown, all of you have to be like either behind there or actually in this corner. The whole point being you want to be accessible from the door. And you stay off your phones.
Activate lockdown immediately. Activate lockdown immediately. Activate lockdown now. Activate lockdown immediately. Activate lockdown immediately. Activate lockdown now. Activate lockdown immediately. Activate lockdown immediately. Activate lockdown now.
Attention all staff and students, lockdown is all clear. Lockdown is all clear. The lockdown is now canceled. Thank you everyone for participating in the lockdown drill. This was a drill. In the event of a real lockdown, you would not hear somebody ringing or knocking at your door or shaking your door handle. If you are outside of the building, your secondary site is the church across the street, St. Adam's. Thank you for participating. The lockdown drill went very well. Teachers, please stand by for an email.
Okay. Okay, so back to this. We drew the Lewis diagram for them separately, and you can see what's going to happen here. What's lithium going to do to become an ion? To react with fluorine, it's going to do what? It has to give. It's only got one. It's easier to give one than to get 7 from fluorine. And fluorine isn't interested in that. So, whose notes are those? Who's got his stuff?
It's mine.
Where's his? Okay, gentlemen, figure out your stuff. This one is going to leave. It's going to join over here. And now we redraw. Lithium will be empty, charge of +1. Fluorine will be full, 1, 2, 3, 4, 5, 6, 7, 8. Charge of -1, and you're done. And just like with the board diagrams, I didn't tell you specifically, but now I will tell you specifically. If you've got a bunch of positives and negatives, you're going to arrange them so that the thing goes plus, minus, plus, minus, plus, minus, plus, minus. Because the like charges, as you learn in grade 9, like charges repel, opposite charges will attract each other. So that is the Lewis diagram, the procedure for a Lewis diagram, and everything I want to see for an ionic compound. The covalent ones look a little bit different. So here's an example for a covalent compound. You've got O2. O2 means you've got 2 oxygens there, and oxygens are nonmetals. So this thing is going to be, that's a nonmetal, nonmetal. This thing's going to be covalent. And so this is the new one. This is where things are going to get a little bit weird. Because you've got a nonmetal, we want to draw them sharing. So let's draw our 2 oxygens. There's one O, there's another O. The symbol for oxygen is O. And the thing is in group 16. So it's going to have 6 valence electrons. Again, how you've got to place them one at a time on the 4 sides and then start pairing them up. But the order you pair them up in can be different. It doesn't have to be the same order you put them down in. So 1, 2, 3, 4, and now I need to place 2 more. You can see that I'm going to have to draw them kind of towards each other. So what I'm going to do is I'm going to have that pair go there and this pair go here. I've got 1, 2, 3, 4, 5, 6 on this oxygen, and now I'm going to have 1, 2, 3, 4, 5, 6 on that oxygen. And now covalence share. Just like with the board diagrams, we wanted to circle the sharing pairs between them. So this pair will share, and this pair will share. And here's the difference. In a Bohr diagram, we would redraw now with overlapping orbitals. That gets cumbersome and kind of clunky. What we're going to do now is when we redraw this thing, I'm going to have 1 O there and 1 O there. Each one of these circled things, circled pairs, gets represented by one single line. That line to represent that pair, this line to represent that pair. And then you draw 1, 2, 3, 4, 1, 2, 3, 4. The electrons that were around the outside stay around the outside. The circled ones, that circled pair becomes that line. That circled pair becomes that line. For small things like this, I mean, we could have drawn a board diagram for this and it wouldn't have been the worst thing we could have done. It's unpleasant, certainly. But it's, yes. For things like this is where board diagrams get really useful, because instead of doing circles on circles on circles, carbon, hydrogen, and oxygen all share. The thing looks like this. 1, 2, 3, 4, 5, 6. Hmm. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 7, 8, 9, 10, 11, 12, and you just draw lines between each one of these things. You don't have to draw this out now, but instead of drawing all the board diagrams with all the looping, this is all you have to draw for a big compound like glucose. And you can get you can show a lot in there in a very short period of time. So this is the end of what we're doing today. Lewis diagrams. So what I want you to do is I want you to draw, you're going to practice a bunch of these. I've got 5 of them that I want you to do, and you got 20 minutes, which is way more time. So you're going to start here and crank out these guys. I've actually got more than 5. I'm going to add 5 or 4 more. I'm going to add a couple more. 4 more. Once you've done those ones, showing me all the work, I want you to try these ones as well. I want you to draw me a PBr3. I want you to draw me an N2H2. I want you to draw me a CH3OH. And I want you to draw me a C2H4. The first 5 are nice and easy. These last 4 are a little trickier. So you got 20 minutes, 9 questions to take a look at. Let me know how I can help you, if I can help you, and on your market site giver. That is all.